Hello everyone, welcome on our YouTube channel Physics Made Easy Kota. In this video lecture, we are going to learn about the chapter electromagnetic induction. Here are the topics which I am going to explain in this first part of the video lecture. Firstly, I am going to explain about the Faraday's and the Henry experiments and their contribution in electromagnetic induction. What is magnetic flux? That is our next topic. Number third, we are going to understand about the Faraday law of electromagnetic induction. Fourth, Lenz law and conservation of energy, and also I am going to explain about the verification of Lenz law. Electricity and magnetism are interrelated to each other. As moving charge produce magnetism, on the similar lines moving magnetic poles can produce electric current. When there is a change in the magnetic flux linked with the closed circuit, there is a production of induced EMF and hence induced current. That phenomena is known as the electromagnetic induction. The term electromagnetic induction means inducing electricity by magnetism. Faraday and Henry performed certain experiments to explain the concept of electromagnetic induction, and there are certain devices like transformers, electric generators that have been developed on the basis of the experiments of Faraday and Henry, and they are also known as the EMI, that is the electromotive induction. Two famous scientists, Michael Faraday and Joseph Henry, conducted experiments to demonstrate that electric currents are induced in a closed coil subjected to the changing magnetic field. Their experiments help to understand the concept of the electromagnetic induction. Here is one of those experiments performed by them. This experiment shows or help to understand the relation between the electricity and the magnetism, and how the magnetism help to induce the current in the circuit. So for this experiment we need certain things, that is coil, galvanometer and a bar magnet. You can easily observe that a coil is connected to a galvanometer. First of all, take a bar magnet and keep it at a one fixed position, which means that the bar magnet is at rest. When the bar magnet is at rest, there is no change in the magnetic field. If there is no change in the magnetic field, then no current is induced in the coil. That is, the galvanometer show no deflection. Now move the bar magnet close to the coil. You can observe that galvanometer shows deflection, but this deflection is in a particular direction when you are taking a bar magnet closer to the coil. Now take a bar magnet away from the coil and keep an eye on the direction of the deflection shown by the galvanometer. When you take a bar magnet away from the coil, again it shows a deflection but in the opposite direction. So again I am going to perform the same thing and just keep an eye on the deflection shown by a galvanometer. First of all, take a bar magnet closer, then away, that is closer and away. You can easily observe that when you take a bar magnet close to the coil, the deflection is in a one direction. When you take a bar magnet away from the coil, galvanometer shows direction in the opposite direction of the previous one. This shows that the galvanometer shows the presence of the current, that is the movement of the galvanometer, and the deflection shown by the galvanometer indicate the flow of the current in the coil when there is a change in the magnetic field of the bar magnet. But when for both the cases we see that there there is a flow of the current but in the opposite direction. When we take the bar magnet closer to the coil, it shows the deflection in one direction. When you take it away from the coil, again it indicates the flow of the current in the coil but in the opposite direction. Now if you increase the deflection of the galvanometer, and the question is how to increase the deflection of the galvanometer, that is just by moving the bar magnet fastly. You can clearly observe that there is increase in the deflection of the galvanometer as you keep on moving the bar magnet close to the coil, away from the coil fastly. And now for the next case, now just flip the magnet, that is take the south pole of the bar magnet closer to the coil, or move it close to the coil, move it away from the coil, move it little bit faster, increase the movement of the bar magnet, and just keep an eye on the deflection shown by the galvanometer. And again I am going to perform the same concept. Just take the bar magnet closer to the coil, then away from the coil. We see that galvanometer show deflection, but in this time it is in the opposite direction as compared to that shown with the similar movement of the magnet when the north pole is facing towards the coil. So this is the final result that we get from the experiment. Our experiment deals with the position of the magnet and the deflection shown by a galvanometer. So when a magnet is at rest, no deflection in galvanometer. Number 2, magnet move towards the coil, deflection in galvanometer in one direction. Number 3, magnet is held stationary at same position near the coil. Again, no deflection in galvanometer. Galvanometer show deflection in opposite direction when magnet move away from the coil. If you keep the magnet held stationary at a same position away from the coil, again no deflection is shown in a galvanometer. So Faraday conclude that whenever there is a relative motion between a conductor or a coil and a magnetic field, the flux linked with the coil changes, and this change in the flux induces a voltage across a coil or EMF. Consider a small surface of area capital A. Let the unit vector be drawn which is normal to the plane of the surface. If theta be the angle between the unit vector and the uniform magnetic field, then the magnetic flux is defined as phi is equal to BA cos theta. Actually, magnetic flux is defined as the total number of magnetic lines passing through a given surface. Magnetic flux is a scalar quantity and its SI unit is Weber. And Weber has also a definition in respect to the quantities involved in defining the magnetic flux. So it is a flux produced when uniform magnetic field of 1 Tesla crosses normally an area of 1 meter square. And the CGS unit of magnetic flux is Maxwell. Weber and Maxwell has a relation that we can convert one system of unit into another. That is 1 Weber is equal to 10 raised to power 8 Maxwell. Faraday performed experiments, and on the basis of his experiment, he defined the law of electromagnetic induction. There are two laws of electromagnetic induction. The first one is known as the Faraday's first law of electromagnetic induction, which is also known as the qualitative law. This law states that whenever magnetic flux linked with a closed conductor changes, an EMF is induced in it, and this induced EMF lasts so long as the change in magnetic flux continues in the coil. Second law, also known as the quantitative law. the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the conductor, and it is also defined mathematically that the magnitude of induced EMF is equal to d phi divided by dt. Here phi represents the magnetic flux that keep on changing, and both are directly proportional to each other. Now we are going to understand about the Lenz law. So firstly, what is the statement of the Lenz law? This law states that the polarity of induced EMF in a closed circuit or a coil is such that it opposes the cause which produces it. Suppose we have a bar magnet and we are moving the bar magnet towards the closed loop. As you keep on moving the bar magnet towards the loop, of course the magnetic flux link with the loop increases with increase in the magnetic field. But if you observe the diagram that shown in this video, that is in the given slide, if you try to increase the flux through the loop, the induced field will oppose the increase, and if you try to decrease the flux through the loop by moving the bar magnet away from the loop, then the induced field will replace that decrease. So it means that the polarity of the induced EMF in the closed circuit is such that it always opposes the cause which produces it. That is, the induced magnetic field will always oppose the change in the magnetic flux that is producing it in the loop. According to the Faraday's law of electromagnetic induction, we have a relation of the induced EMF, and here the negative sign is a significance or the importance of the Lenz law. The negative sign shows that the induced EMF opposes the rate of change of magnetic flux in a closed circuit. Now we are going to understand the Lenz law with one of this small activity. Consider a bar magnet moving towards a closed loop as shown in the figure A. As the bar magnet keep on moving towards the loop, then we know that the magnetic flux linked with the loop increases with increase in the magnetic field. And according to the Faraday law of electromagnetic induction, induced EMF is set up in the closed loop, causing electric current to flow in the loop. And the Lenz law, how we can forget that? It states that the direction of induced current in the loop is anti-clockwise, so that the magnetic field produced inside the loop due to induced current opposes the increase in the magnetic field of the approaching bar magnet. So the face of the loop towards the north pole of approaching bar magnet behave as a north pole, and we know that like magnetic poles repel each other, therefore the motion of the bar magnet towards the loop is opposed. Now observe this diagram. In this diagram, a bar magnet is moved away from the closed loop. So the magnetic flux linked with the loop decreases with a decrease in the magnetic field. Therefore, induced EMF is set up in the loop, causing induced current to flow in the loop. And according to the Lenz law, the direction of induced current in the loop is clockwise as seen from the side of the magnet, so that the magnetic field produced inside the loop due to induced current opposes the decrease in magnetic field of a bar magnet moving away from the loop. Thus, the face of the loop towards the north pole of a bar magnet moving away from the loop behave as a south pole, and we know that unlike poles attract each other, therefore the motion of the bar magnet which is going away from the loop is opposed. So in this way, it always opposes the cause from which it is produced, which means that the direction of the induced current in a closed circuit is such that it opposes its cause. Fleming's right hand rule. This rule is also known as a generator rule. Why we are going to learn about this rule in this video? Because this rule helps us to find the direction of the induced EMF or current in a circuit moving in a magnetic field. So according to this rule, if the right hand is stretched such that the first finger, the central finger and the thumb are mutually perpendicular to each other, then the first finger points along the direction of magnetic field while the thumb points along the direction of the motion of the conductor, then the direction of induced EMF and hence current will be along the direction of the middle finger. In nutshell, you can say that the direction of the field along the first finger, direction of motion along the thumb, and the direction of induced EMF or current along the central finger. We know the law of conservation of energy, which states that energy can neither be created nor destroyed but can be changed from one form to another. To explain the Lenz law in accordance with the law of conservation of energy, we consider an example, or you can say that a very simple experiment in which we have a bar magnet and a coil which is attached to the galvanometer. In the above experiment, where north pole of a magnet is moved towards the coil, the right face of the coil acquires north polarity as per Lenz law. Therefore, work has to be done against the force of repulsion because like poles repel each other, and we have to do this work to overcome or against the force of repulsion in bringing the magnet closer to the coil. Now for the same experiment, when the north pole of a magnet is moved away, south pole develops on the right face of the coil as per the Lenz law. Therefore, work has to be done now against the force of attraction in taking the magnet away from the coil. This mechanical work in moving the magnet with respect to the coil changes into electrical energy producing induced current. Hence, energy transformation takes place, and we can say that Lenz law is a consequence of the conservation of energy. Now it's a time to verify the Lenz law that we already studied. Now for the verification of the Lenz law, we have an experimental setup. It consists of a coil connected to a battery and a galvanometer through a two-way key 1, 2 and 3, and also it consists of a bar magnet. Before this experiment, we must remember the few concepts that if a magnetic flux linked with the coil loop increases, current in the loop is anti-clockwise, and if the magnetic flux linked with the coil loop decreases, then current in the loop is clockwise. So now for the experiment, the step number 1, close the key by inserting a plug between 1 and 2. The current flows in the coil. The current through the upper face of the coil flows anti-clockwise. So this face of the coil acts as a north pole and the galvanometer shows deflection. Let the galvanometer show deflection to the right side. Now we are going further for the step number 2. Now remove the plug from the 1 and 2 and insert it between the points 2 and 3. The battery does not send any current in the coil because now the battery is unplugged. Now move a bar magnet towards the coil with its north pole pointing towards the coil. You see that the galvanometer shows a deflection towards the right side. It indicates that the induced current through the upper face of the coil is in a clockwise direction, and hence upper face of the coil acts as a north pole. It opposes the motion of the magnet towards the coil, which is the cause of the induced current in the coil. Now further, step number 3. when the magnet is moved away from the coil. Galvanometer shows a deflection towards the left side. It indicates that the induced current through the upper face of the coil is in clockwise direction, and hence upper face of the coil act as a south pole. It opposes the motion of the magnet away from the coil, which is the cause of the induced current in the coil. So we conclude that the induced current in the coil opposes the cause, that is change in magnetic flux, which produces the induced current. This verifies the Lenz law, and hence Lenz law is verified.